The example I'm using today is the pattern on the heads of snakes. The three phenotypes are plain versus split versus the double split. Dominant alleles are the big A and the big B, and the recessive are the little a and the little b. An image to better understand this, we have the plain split and the double split. The expression of a dominant allele of A allows for the expression of split, and then also with the dominant expression of B allows for the double split. Any expression of a homozygous recessive gene stops the expression of the second one. So at the first stage, if there is a homozygous expression of A, it doesn't matter whether the B expresses recessive or dominant alleles, it's going to stay plain. If it expresses a single dominant A, it can express the split. And if it expresses homozygous recessive B, it's going to only exhibit split. And then to be double split, it has to express both A and B enzymes, which are the dominant alleles. In a stereotypical dihybrid cross, it's typically 4 phenotypes are expressed at a 9:3:3:1 ratio. When single recessive epistasis occurs, at A, there's a 3/4 chance of expressing the dominant A, while there is a 1/4 chance of expressing homozygous recessive A. Just from that 1/4 expression, those be the ones that will stay and only express the phenotype of plain. The 3/4 that move on to look at the B will have a 3/4, 1/4 split of expressing dominant B versus homozygous recessive B. The 3/4 that express this enzyme B, the dominant allele, would move on to express the double split. That 1/4 expression are the plain, and then 3/4 that move on to the intermediate times the 3/4 that move on to the double split would be the 9/16 expression chance of being double split. This intermediate stage, 3/4 have a chance to move to the intermediate stage, and 1/4 of those will express homozygous recessive and be the intermediate stage, which is the split, which this results in a 9:3:4 ratio, which you can see is different and doesn't have that 4th phenotypic expression.